This is the Waves Homework Booklet, question 22. As you read this question, you should try and match the information given in the text to what you can see in the diagram. We are told that we have a 45-degree right-angled glass prism. From that we know that we have 90 degrees here, 45 degrees here, and this angle here must also be 45. The prism is supported by a film of liquid on a glass table. So looking at the diagram carefully, there's the liquid and there is the glass. Monochromatic light is incident on the prism at an angle of incidence of theta degrees and emerges along the glass liquid boundary as shown. First of all, we are asked to calculate the speed of light in the glass. We know the refractive index of the glass is 1.5. The definition of the refractive index of a substance is the ratio of the speed of light in a vacuum divided by the speed of light in the substance. This is the speed we are looking for, so we can rearrange the equation and substitute in the speed of light, 3 times 10 to the 8 meters per second, and the refractive index of glass. This leads us to an answer of 2.0 times 10 to the 8 meters per second. It is worth just checking that our answer is sensible. Clearly, if you got an answer higher than the speed of light, you know you've made a mistake. Next, we're asked to determine the angle of incidence theta. This was shown in the diagram. It's a straightforward application of Snell's law across this boundary. So n1 sine theta 1 equals n2 sine theta 2. n1 corresponds to the air, so it is 1. n2 was the refractive index of the glass, and theta 2 is the angle of refraction. This gives us a value for sine theta, and so we can simply solve to find the angle theta. Notice that I have given the final answer to 2 significant figures. That is because the number 15 was given in the diagram to 2 significant figures, so it would not make sense to claim any more. Next, we are asked to find the refractive index of the liquid. So we are now considering the ray as it moves from the glass towards the liquid, and we can apply Snell's law across this boundary. We notice that the angle of incidence must equal the critical angle. This is because the ray has got an angle of refraction of 90 degrees and passes along the boundary between the two media. Substituting that information into Snell's law, we have the refractive index of glass and our angle of incidence at this boundary of 60 degrees, and we have our unknown refractive index of the liquid and sine of 90. You could use the equation in the datasheet for the critical angle if you wished. Substitution and rearrangement leads us to a refractive index of 1.3. Once again, this is appropriate to be given to 2 significant figures based on the data that we used. Finally, we are told the liquid is changed to one with a lower refractive index and asked to draw a possible path for the ray beyond the point A and into the air. Notice the detail here, we do actually want to show 2 parts of the ray's journey. Looking back at the diagram, it is clear that if this liquid had a lower refractive index, that total internal reflection must take place. So you draw a reflected ray, making sure that this angle is looking very close, preferably identical to this one. So you must obey the law of reflection, and then you want to show refraction as the ray leaves the glass and once again emerges in the air. This is moving towards a lower refractive index, so the light must bend away from the normal as shown. If you look more closely at the angles in the diagram as a whole, we know that this angle is 45 and that this angle is 30, and we can work out that this angle here must therefore be the same as this one, as we have two triangles with equal angles. That means that the angle of refraction in the air is actually identical to the original angle of incidence. You need to draw your diagram carefully to show that that's what you intend.